in section 4.3, I'll come back and fill in these notes. If I don't have time in class today, then I may even do it in a video online and let you come back and see it as part 2. This is just the order that I had originally done it whenever it was split between one day and the next. It was a good way to start a lecture. We'll now send this to your screen. I am recording. So, let's start simple. We'll build up. Let's talk about a second order equation. So instead of nth order, we're going to start with just a smaller level problem of only doing second order. So it looks like this. But the other thing we're going to do now is simplify it even further. Constant coefficients. So instead of having a1 of x and a2 of x and a0 of x, that is the coefficients in front of the y's depending on x, let's start even simpler with that because we have a very complete and easy to use theory that gives me a very quick way to find the solution to this. So starting with a homogeneous, second order homogeneous linear equation with constant coefficients. So the a, b, and c don't depend on x, they're just numbers. The question is, can we find the solution? And you've actually done this. This is the problem that I told you that you did on the test and on the review. I asked you if your solution was of a given form. Can you find the m's that make that true? Do you remember that problem?
Yeah.
Vaguely at all? I already closed the browser. I'd go back and look at it. Okay. I gave you something like y double prime minus, say, 3y prime plus 2y equals 0. That's just a simple example. And I said if y equals e to the mx, find m so that e to the mx is a solution. So all you did was you took the first derivative, second derivative, you plugged in. What ended up happening is this thing turned into a quadratic equation. Because you could factor out the e to the mx of every single term, and what was left was just the quadratic equation. In fact, it had the same coefficients as your differential equation, interestingly enough. Well, that's the technique. Okay? That helps us, that actually finds linearly independent solutions to this differential equation. So we're going to use y equals e to the mt, I'm just using t as my variable now in my notes for some reason, as a solution, and so that we hypothesize that our solution is going to be of that particular form, namely y equals e to the mt. All I'm saying is right here, this is kind of where we get the idea. Back when we did this basic kind of problem, y equals a constant, y prime equals a constant times y, we found that the solution was y equals e to that constant times t. Okay, so what values of m does this actually make a solution? So plug it in. Y prime becomes m e to the mt, and y double prime becomes m squared e to the mt. So now if we start with ay double prime plus by prime plus cy equals 0, okay, I'm going to stick this in here. I'm going to stick this in here. And I'm going to stick, of course, this in for just y. So you get a times m squared e to the mt plus b times m e to the mt plus c e to the mt equals 0. Now I'm going to pull e to the mt out of all of these. And what are you left with? am squared plus bm plus c. And to solve an equation where two things are multiplied together to equal 0, you set each one equal to 0, right? Well, this guy right here is never 0. Which means this solution is equivalent to am squared plus bm plus c equals 0. If I can solve that for m, a, b, and c, remember, are given in the problem. They're going to be numbers. Like up here they were, at the top of the page I wrote 1, -3, and 2. This, by the way, has a name. It's called the characteristic polynomial. Particularly of that equation 2 at the top of the page. So this word right here is important. We'll talk about the characteristic polynomial frequently. But you know how to solve that, right? How do you solve that equation? In general, what's your strategy for solving an equation that looks like that? Factor. What if it doesn't factor? Quadratic formula. Quadratic formula is the sledgehammer that will always work. Factoring works occasionally. You use factoring if you see it and can factor it. But if nothing else you can do, that right there. You can sing it in your head. I'm not going to sing it for you. You know the song, right? X, I have to sing it now. X is equal to negative b plus or minus the square root of b squared minus 4ac. Thank you. Woohoo! Putting that one on YouTube just as a clip, just for that. Taking that out. That's going to be an excerpt. I might even Vine that thing. Okay. Now, there's 3 actual cases that will give us distinctly different looking types of answers. Like whenever you solve a quadratic equation, you can get, the best case scenario is 2 real roots, right? Whenever the thing underneath the radical, which by the way has a name. Do you remember what the name of the thing under the radical is in the quadratic formula? Close. Determinants are matrices, but it is a D word. Kind of sounds like determinant.
Sorry, what did you ask?
What's the name of the thing under the radical? We give it a name. We give lots of things names in mathematics. You should remember your vocabulary.
They never told us.
Oh, liar. Discriminant. It's the discriminant. Yes, they did. Liar. All right. You were mistaken. Now you are informed again. The discriminant. If it's positive, you have 2 distinct real roots. The nice thing about 2 distinct real roots, if I call them M1 and M2, and they're not equal to each other, then what that says is e to the M1t is a solution. And y2 equals e to the M2t is a solution. And although I'm not going to check it, you can do so with the Wronskian. They are linearly independent. If M1 does not equal M2, obviously they are dependent if M1 equals M2, because they are the exact same function. So you then have 2 linearly independent solutions to a differential equation. And if you have 2 linearly independent solutions to a homogeneous equation, what is that set called?
Fundamental.
It's the fundamental set of solutions, which means then that your general solution, y, is C1, y1 plus C2, y2, and you are done. There's actually no calculus or differential equations involved at all in solving a second order linear ODE with constant coefficients. All you're really doing is solving a characteristic polynomial, which is a quadratic equation, and then writing down the answer. Done. Easy peasy. All right. What about if the discriminant is 0? One single root, okay? Or what we sometimes call a repeated root, because if we were to factor this thing, it's a binomial squared, because you get the same root twice. Okay, so you have one root repeated. In other words, M1 equals M2. Well, now we have a problem. How do we get a second solution? Because I can't write y2 equals e to the m2t because it's the same solution again. I don't have two independent ones then. So, as a gift to you, I'm going to tell you what it is. I'm not going to make us find it or derive it. I'm just going to hand this to you. You could easily verify that it is in fact true, but turns out all you got to do is this. If M1 is a repeated root, try e to the M1t with a t out front. That also solves it. It only solves it whenever M1's a repeated root, but it does work. You want me to show you that it works?
No.
You want to trust me?
Trust you.
It's unfortunate. Y'all answered that incorrectly. The right answer is, I don't believe you, Dr. Franklin, until you prove it. But since you're going to let me get away with it, I'm going to get away with it. These are linearly independent, which means if you get a repeated root, your general solution is C1 e to the m1t plus C2t e to the m1t. You should not be able to sleep tonight until you've tried plugging this in to that differential equation, number 2 above.
I'm pretty sure it's different.
No, you can't. It's like, you know, the princess and the pea. It's the mathematician and the unsolved proof.
I never lost a week of sleep.
You bunch of engineers. Come on. Killing me here. All right. Now, what if the discriminant is negative?
There's no roots.
Oh, no. That's what we told the basic, high school algebra students when they first saw the quadratic formula. But we all know better. There is solutions, right? What are they?
Not really.
Not real. Call them complex. I don't like the word imaginary, but people use the word imaginary for that unit. Imaginary makes it sound like we're just making stuff up as we go along, but we're not. It's an actual, very real, but not real, but real solution. It's important. In fact, the value of this solution allows your cell phones to work, allows you to drive across a bridge without it collapsing, allows you to fly in a plane. If we didn't have complex numbers, you could do none of those things. Okay? They're very important. Very important. Okay. Complex numbers, right? So we get two complex numbers. In fact, they're associated with each other in that they are complex conjugates. Remember the word conjugate?
Yes.
Not conjugate from your Spanish class, but conjugate. It is A plus or minus BI. Right, that's M1 and M2, right? M1 is A plus BI, M2 is A minus BI. All right, now, Y1 would then be E to the A plus BI T plus, sorry, I see one out. No, that's just Y1, not plus. We'll do the plus in a second. Comma, Y2 is E to the A minus BI T. So, the general solution is C1 E to the A plus BIT plus C2 E to the A minus BIT. That C needs to go on the outside, by the way. Now, just as a comment here, one thing that we could easily do to separate this out is to recognize that e to the a plus bit, I could distribute the t inside here, and this would be the same thing as e to the at times e to the bit, right? Where, I is not a subscript in this case. Remember, I is the imaginary number. I is the solution to that equation. Okay? The number that when squared gives you -1, by definition. I mean, if every time we came up with a new number in mathematics to answer a question that we didn't have an answer to, we called it imaginary, then 0 would be a pretend number. Because at some point we had to describe 0 as the absence of something, when for the majority of the history of mankind counting, we did not have a number for 0. And then when we start talking about negative numbers and what it means to have a negative of something, when we subtracted a larger number from a smaller number, we had to invent a new kind of number. We didn't call those imaginary. We gave them a name. We called them negative numbers. And then we started dividing things where we needed to take whole things and divide them into pieces, but then the pieces were smaller than the whole itself. We created fractions. We didn't call those imaginary whenever we made them up. We gave them a name, fraction. So why did, whenever we needed something to describe the square root of a negative number, we decide, let's pretend and call it imaginary? That's ridiculous. You should have given it a good name, like, I don't know, what's a good name for an imaginary number? A quaternion, which we actually called these things, but in other contexts. What did you say?
Did you say Sean?
Sean. We could have called him Sean. In fact, we should. From this point forward in this class, this is Sean.
Well, if we're going to call him Sean,
I mean, complex numbers are a real part plus Sean's part of the number, okay? Add those together, you got a complex number. Just don't...
Wow, he has good things about this.
This dude here, no longer called imaginary unit, is Sean. Is that Sean with an S-E-A-N or a Sean like Sean the sheep?
Sean like M-R-W-A-Y-L-A-N-D.
That works.
All right, we're being silly. Let's move on. Now, that means I write this solution as I'm going to pull out the e to the at out of both of those and write it as C1 e to the bit plus C2 e to the negative bit. And despite my love for Sean, or the imaginary unit, or the complex number made up of this I, this dude, the problem is I started with a nice real, like in real number, real differential equation. So why should my solution now involve complex numbers? Can I write it as a real valued function, or does it have to actually be a complex valued function? The hope is that this is in fact a real valued function that's a solution, even though I've got i's showing up. What I mean by real valued is if I plug in a number t, like a time, at time t equals 0 or time t equals 3, I don't want to get a complex number as an output, because this may represent something physical. In fact, the part I skipped over on page 1 is modeling a spring with a mass attached to the end to it. You pull the spring out and let the thing go, and it bounces back and forth. Okay? If I plugged in, where is that mass at time t equals 3 seconds, I shouldn't have a complex number. It should have not left the real world and gone into the complex plane. It still needs to have a real valued location, even though my functions, in this particular case, appear to have an imaginary part to them. The good news is, there's a dude solved this problem for us.
What a guy.
Euler recognized a very important formula that shows a relationship between e to the theta I and cosine and sine. This is called Euler's formula. I proved this in trigonometry. It's actually a very nice result that shows that these guys and their periodic nature have a connection to e to the theta I. You can also see this immediately if you use if you use power series. You remember power series? I'm pausing.